All right, so for tutorial 5, question number 1, we are asked to sketch the waveform of this digital signal 110101 modulated using the following modulation scheme. All right, so for binary ASK, binary FSK, and binary PSK. All right, so this one again, you can find it in here. All right, so again, I'm going to use, as far as ASK is concerned, right, my binary data is 110101. Right, 110101. And for ASK, 1, we actually send with a pulse. All right, send the carrier signal if we are sending a binary 1. And then for binary 0, we don't send anything. There's no carrier. All right. And then the other thing to take note is the frequency of your carrier signal can or must be n times the frequency of your bit of your signal of your baseband signal. All right. So in this case, if your bit duration is given by TB, then your carrier frequency has to be n over TB. Right? TB is your bit duration. So in this case, I'm going to use n equals to 1. All right, in this case here, n equals to 1. That means for every bit, I just send 1 pulse. All right, you can also choose n equals to 2. In this case, you actually send 2 oscillation. All right, so what I'm going to use, I'm just want to send 1 pulse. Yeah, so for binary 1, I send 1 sine wave. You can also send cosine wave. All right, but again, just to draw easily, I use sine wave one. Yeah, so binary 1, I send a sine wave. Binary 1, I send another sine wave. Binary 0, nothing is sent. Yeah, that's ASK, nothing is sent. And then for binary 1 again, I send another sine wave. Binary 0, nothing. Binary 1, another sine wave. All right, and then for PSK, I'm going to send PSK using PSK, a binary 1 with no phase shift. All right, and binary 0, I send with 180-degree phase shift. Yeah, so again, I'm going to use the sine wave to send a binary 1. Okay, I just send 1 sine wave. Binary 1 sine wave, 0-degree phase shift. But for binary 0, I'm going to send the sine wave with the 180-degree phase shift. 180-degree phase shift, that means positive become negative. Right, so this is my negative sine wave. All right, to send a 0. Yeah, and to send a 1, I send back the sine wave with 0-degree phase shift. Send a 0, I send a sine wave with 180-degree phase shift, so that is minus sine wave. All right, I send a 1, another sine wave again with 0-degree phase shift. So that's for PSK. All right, and then for FSK, I'm going to send 1 and 0 with different frequencies. Yeah, 1 and 0s are sent with 2 different frequencies. This is 2 FSK. So to send binary 1, I'm going to send a higher frequency signal, which is 2 times the frequency of a 0. So 0, I'm going to send with a lower frequency. Yeah, and then of course this n, this 2, again you can also use 4 if you want. Yeah, but it has to be the multiple of the frequency that you use to send 0. Yeah. So for to send a binary 1, say I'm going to send 2 oscillation here. So let's make sure that the frequency of the carrier that I send is 2 times the frequency of the carrier I send for a binary 0. So this is binary 1, 2 oscillation. Binary 0 is only 1 oscillation. Okay, or 1 cycle. Yeah. Okay, so that is for 2 FSK. You want to take that down first? Let me know when you're finished. Yeah?
Yes, done this.
Okay. So let's move on to second question. So in second question, question number 2. What's question number 2? Okay. In question number 2, we have a Qpsk or 4psk, have a phase shift of 90 degree or pi over 2 radian for each 2-bit symbol as shown in the following formula. All right. So the signal equation for Qpsk is given by this one over here. All right, so to send a 2-bit symbol, which is 0, 0, we actually send a cosine wave with the amplitude of A, right? And then to send the symbol 0, 1, okay, a combination of 2 bits, 0 and 1, we actually send a cosine wave, amplitude of A, but has a phase shift or phase angle of pi over 2, which is 90 degrees. Yeah. And then to send 1, 0, okay, we also send a cosine wave, same amplitude, and then the phase shift now is pi. Yeah, and 1, 0 is sent with a phase shift of 3 pi over 2. Yeah, so first one, you need to sketch the constellation diagram. Yeah, so in your practical session, you don't actually have to sketch, you just click view constellation and straight away show you. Yeah, you need to understand what the constellation diagram means. If you know what it means, then it won't be difficult for you to sketch it over here. Okay, so now to send 0, 0, I send a cosine wave with no phase shift, amplitude is A. All right, so it's this one over here. So if you refer to this diagram, symbol 0, 0 will be sent with the amplitude of A. So that's why this red dot is here. Yeah, and phase angle is 0. Okay, phase angle is 0, so it's lying along this positive side of the x-axis. Amplitude is A. All right, and then for 0, 1, 0, 1, there is a 90 degree phase shift here, which is pi over 2. All right, and therefore amplitude of this one is also A, so therefore 0, 1 is going to lie on this y-axis, on the positive side of the y-axis. This is 0, 1, and the amplitude is A. From here to here, the amplitude is A. Okay, the distance from origin will actually tell you the amplitude. Yeah, and then for 1, 0, 10 is pi radian or 180-degree phase shift. So therefore 10 is here. Yeah, and then with amplitude of A as well. Okay, and then 11 is 3 pi over 2 or minus pi over 2. So that is again with the amplitude of A. So that's why your red dot is here. Okay. So that is the constellation diagram for Qpsk, sent with this. Okay, sent with this phase shift arrangement. And when you did your lab 2, you can still, if you actually sending, let's say if you say I want a phase offset of pi over 2, then you see that this 0 will be sent at a A cosine pi over 2. So your 0 will be here. Okay, 0 1 will be here, 10 will be here, and then 11 will be here instead. If you say I want to send with the phase offset of pi over 4, then your 0 will be here. The 0 1 will be here. Okay, and that is for binary constellation. You also have a choice of gray constellation. I don't know whether you notice or not. If you're using gray constellation, then you'll be the coding or the arrangement will be like the gray code. So 0 0 0 1, then 1 1, then only 1 0. If you pay attention to your Qpsk constellation diagram in your lab 2. Okay, so all right, so I give you a chance to draw this. This is actually very easy to draw. Okay, finish.
Yes, Miss.
All right, so let's move on to part B. Part B, you are asked to draw the actual Qpsk signal for this bit stream with the most significant bit first. All right, with the most significant bit first. And therefore, we need to write down the bit, or before that, because this is a cosine wave, so I'm going to show you how a cosine wave look like first in its original form. So this is A cosine omega ct. All right, and this is your y-axis. Your x-axis is omega ct. All right, so now with the original cosine wave is going to look like this, isn't it? All right, which is going to cross the x-axis at pi over 2 and also 3 pi over 2, right? Because cosine of 90 degrees is 0, right? Cosine of 0 is 1, right? So you have your amplitude A here and minus A here. So minus A not so accurate. So minus A is to be here. All right, this is how your original cosine wave look like. Yeah. So now we need to draw our constellation diagram, and I'll need to draw the waveform, right? The waveform is going to look like this. So, oops, okay, so as far as Qpsk is concerned, we send 2 bit. All right, we send 2 bit at one time. So that means we need to use to draw the waveform for every 2 bits. All right, so 0 0 1 1 0 1 0 1. So to send the first 2 bit, which is 0 0, if you refer to our okay, if you refer to our equation, 0 0 is sent with the 0 degree phase shift, which is this one. All right, so the waveform to send a 0 0 is a cosine wave as it is. All right, again, I'm going to send one full oscillation only. Yeah. And then to send 1 is actually 3 pi over 2. All right, with a phase shift of 3 pi over 2 here. All right, so how to get a phase shift of 3 pi over 2? So I want you to imagine, right, this is the original one. Yeah. So to have a phase shift of 3 pi over 2, that means I have to shift this entire waveform 3 pi over 2 to the left-hand side. Right? So instead of doing that, I'm going to shift my y-axis. All right, I shift my y-axis by 3 pi over 2 to the right-hand side. All right, so if I were to do that, then you can see that my waveform for 1, which is a 3 pi over 2 phase shift, is going to start like this. Okay, it's going to start like this. So it's actually a sine wave. All right, a sine wave. So there you go, a sine wave. Okay, and then for 0, 1, we are going to send, 0, 1, we are going to send with 0, 1, 90-degree phase shift. So for 90-degree phase shift, so I'm going to move my axis by 90 to the right hand side. Yeah, pi over 2. So you can see now my signal is going to start here, like this. Right, this is actually a minus sign. Right, not a minus sign. So I have this, which is a minus sine wave to send 0, 1. Yeah. And then to send 1, 0, 1, 0 is 180-degree phase shift. So 180-degree phase shift means what? From a cosine wave, it becomes a minus cosine wave. So I just have to flip this wave, flip this cosine wave along the x-axis. So positive become negative, negative become positive. So this is my negative cosine wave. All right. Or you may want to again refer to this diagram. You move your y-axis to pi. All right, move your y-axis to pi. So that means your waveform is going to start like this at the negative A. All right, and then you make a full oscillation. Negative A, go to positive A, and then go back to negative A. All right, one cycle. So this is how the Qpsk waveform for this bit stream is going to look like. All right, so I think I continue with the discussion first, then you take down the answer later, yeah? So you are asked to actually, for part C, you are asked to actually, wow. Okay, you're asked to answer this question. What is the advantage of Qpsk as compared to Bpsk? All right, and to actually know the advantage, right, you're going to compare this Qpsk waveform to the Bpsk waveform that you drew up there. So in this 2 PSK waveform, right, 2 PSK waveform, you see, to send 1 bit, we actually use 1 pulse. All right, and to send 2 bits, we need to send 2 pulses. Right, not? We need to send 2 pulses. But for Qpsk, to send 2 bits, you actually need 1 pulse only. You say 1, 1, I only need to send 1 pulse to represent 1, 1. Yeah. So your discussion is going to be like this. By using Qpsk, we can actually send 2 bits in 1 pulse. All right. But Bpsk, we can only send 1 bit in 1 pulse. All right. So that means given the same bandwidth, we can actually send 2 times the bit rate using Qpsk. Yeah. So Qpsk, as far as bandwidth efficiency is concerned, is better. All right. Qpsk is more bandwidth efficient than Bpsk. Oh, do you need this one? Do you need this one? Do you need this one? Okay, let me bring this one down first. Maybe like better. So I'm going to bring this one down. Okay.
Done, Miss.
Okay. So it's 12 o'clock. Let's take a short break, 5 minutes break, shall we? Then we continue after the break, yeah? All right, is everybody back here?
Yes, Miss.
Good. So we're going to continue with the question 3, right? So for question 3, we have binary signaling with the received peak amplitude is 1.5 millivolt. Determine the detection error probability if the channel noise is Gaussian with the RMS value of 0.3 millivolt. All right, assuming 0 ISI, what is the error probability for polar signaling? All right, so to calculate the error probability for polar signaling, you will have to remember the equation in terms of Q function. All right, don't remember the equation involve integration one. That one is very complicated. So the reason for using Q function is because it simplify our calculation a lot. All right. So the probability of error for polar signaling is a Q of A over sigma. All right, Q of A over sigma. So A is 0.0015 and sigma is 0.0003. So that means we need to find the Q of 5. All right, Q of 5. So how do you find Q of 5? Again, you need to make use of your appendix A. All right, where is Q of 5? Which is this one here. Q of 5 is here. Let me enlarge a bit now. Q of 5 is here. All right, Q of 5 is here. So that means our Qx is 2.8665 times 10 to the power of minus 7. So that's our probability of error. All right, so I round up to 2.87. Okay, and then for polar on-off signaling, the probability of error is Q of A over 2 sigma. All right, and then same thing, putting in the values, then you need to find Q of 2.5. All right, so where is Q of 2.5? Q of 2.5 is here. All right, X is 2.5. What is QX? Yeah, so that is 0.0062097. So again, I round up to 6.21. 6.21 times 10 to the power minus 3. Yeah. And then from these two results, you compare and see, you can see that polar signaling actually give us better bit error rate or probability of error. Yeah, as compared to on-off. As for probability of error, always remember the smaller the number, the better. All right, in this case, the smaller the number, the better. Because I say the chances of error is very small. Chances of error is very small, that means your system is good. This one, the chances of error is bigger, right? So your system is not so good. Okay. When you're done, let me know.
Done, Miss.
Okay. So moving on to part B, you need to determine the received power in each case, assuming half-wave rectangular pulse. All right, half-wave rectangular pulse. So again, to help in your understanding or to visualize the problem, half-wave rectangular pulse is going to look like this. All right, and then we need to work in terms of polar as well as on-off. So for polar half-wave rectangular pulse, to send a 1, we send a positive pulse that lasts for half of the bit duration. That is for a binary 1. For a binary 0, we send a negative pulse, also lasts for another half bit duration. And then the second half of the bit duration, we send 0. Okay, the amplitude is 0. So again, if you compute the power of a binary 1 pulse, the power basically is V squared over R, right? So again, in this case, we're going to take R as 1. So because this pulse lasts for only half of the bit duration, so the power is half, like A squared over 2. All right, and then the binary 0 pulse, okay, again, amplitude square, negative will become positive. So that gives you A squared over 2 as well. So the average power for polar half-wave pulses is A squared over 2. Right? We take the average of these two is A squared over 2. And putting in the numbers, that will give us 1.125 times 10 to the power of minus 6 watt. All right, so that is for polar half-wave. Then if you are asked to calculate energy per bit, then you just take the power, the average power multiplied by TB, the bit duration. That will give you the energy per bit. And then for on-off case, all right, for on-off case, again, to simplify our calculation, we're going to assume that the probability of sending 0 and the probability of sending 1 are the same. They are at 0.5. Okay, so that means half of the time we are sending 0, half the time we are sending 1, because they would help us to calculate our average. All right. So in this case, for on-off signaling, to send 1, and then with a half-wave, to send a 1, we actually send a positive pulse. All right, then lasts for the half-bit duration. That's to send a 1, but to send a 0, because it's on-off, that means to send a 0, we off the pulse. Okay, we don't send anything when we send a 0. Yeah. So taking the power as far as binary 1 pulse is concerned is A squared over 2. Right, and then this is A. I've got to write the A here. This is A. This is 0. All right, and then power of power required to send binary 0 is 0. We don't send anything. That was 0. So taking the average, the power will be A squared over 4. All right, A squared over 4. And putting in the numbers, that will give us 0.5625 microwatts. All right. And then from these two answers, you should be able to recognize that with the same pulse amplitude, the power of polar signaling is every 2 times the power on-off signaling.
Done, Miss.
Okay, thank you. So let's move on to the next one here, part C. So in order to receive the probability of error identical to that in the polar case, what must be the receive power for the on-off case? All right. So the probability error for polar case is this. So now we want the on-off case also to have the same probability of error. Okay. So to achieve that, that means the Q of A over 2 sigma must be this value. Yeah. So again, to get this value, the X must be 5. Right? That means A over 2 sigma must be 5, isn't it? Because from the previous one, we know that to get, if you cannot remember, let's get back here. So to achieve the same one, which is this one over here, your X must be 5. Yeah. So the X being 5, that means A over 2 sigma is 5. Yeah. A is 10 sigma, which is 3 millivolt. All right. Again, for on-off case, the power equation is A squared over 4. All right, so that gives us 2.25 microwatt. All right, 2.25 microwatt. So you can see if you compare the on-off case now, all right, the power required to have this probability of error similar to the polar case is 2.25. And if you look at the polar case is 1.125, isn't it? 1.125. So therefore, we can actually conclude that the power required for on-off keying is actually double the power required for polar to achieve the same probability of error. Yeah. Or in terms of dB, it's actually 3 dB extra. So this actually proof that the theory that we learned right in the lecture note in lecture is correct. Right, to get the same probability of error for on-off case, the on-off signaling need to be sent with 2 times the power of a polar signaling. Okay, 2 times in dB means 3 dB extra. Yeah.
Done, Miss.
Okay. All right. So let's move on to question 4. So for question 4, we again have a half-wave rectangular pulses transmitted at the rate of 10 kilohertz using an on-off scheme. All right, the detection error probability is required to be less than 10 to the power of minus 6. RMS value of the channel noise is 1 millivolt. Signal attenuation over the channel from transmitter to receiver is 30 dB. Determine the minimum signal power that must be transmitted. All right, and then for simplicity, assume the power shape remain unchanged during the transmission. Okay, half-wave rectangular pulse using on-off scheme. So for on-off scheme, first thing you need to get is what is the probability of error equation for on-off scheme? For on-off scheme is Q of A over 2 sigma, right? Yeah. So the probability of error for on-off scheme, which is Q of A over 2 sigma, must be less than 10 to the power of minus 6. All right, must be less than 10 to the power of 6. That's the first thing you need to write down. And then you need to look up in the Q function table. All right, what is the X value for Qx to be less than 10 to the power of minus 6? All right, so if you come here, okay, the last value in 10 to the power minus 6 is this one. So to be better, then you need to go to this number. All right, for the probability of error to be less than 10 to the power of minus 6, that means your x must be 4.8. All right, must be 4.8 or even more lah. So we're going to take the first number, which is 4.8. So that will give you your A over 2 sigma must be greater or equals to 4.8. That means your A must be greater or equals to 9.6 sigma. All right, 9.6 sigma. And we know our sigma is 1 millivolt. So therefore our A, the minimum, okay, the minimum A, the minimum amplitude must be 9.6 millivolt. All right, 9.6 millivolt. And this is the A, this is A is the amplitude of the signal at the receiver. All right, amplitude of the signal at the receiver. Therefore, we're going to calculate the power. All right, the power at the receiver. Again, this is half wave. Half wave, then the power is, equation is A squared over 4. Right, for on-off keying, A squared over 4. So that means A is this. So square it, divide by 4. That will give you 23.04 microwatt. All right. If you convert to dB, is minus 46.38 dB. 38 or 39, somewhere there. Okay. So now this is the power at the receiver. We are asked to determine the power that must be transmitted. All right. Given the attenuation over the channel is 30 dB. So what it means is from transmitter to receiver, okay, the power loss is 30 dB. All right, the power loss is 30 dB. So what is the power at the transmitter? So you need to add back. Okay, you need to add back. So that means minus 46 plus 30, that will give you minus 16 dB. All right, and that if you convert back to watt, then that will be 23.04 milliwatt. All right, another quick way of calculating it, you know, if you're aware that 30 dB is equals to 1,000 times, then you just multiply your receiver power with 1,000, that you get your transmit power. Right, correct or not? 23.04 microwatt multiplied by 1,000, you get 23.04 milliwatt. So that is for on-off keying half wave.
Miss.
Okay, good. So let's, I think the second part, I asked you to repeat A with full wave rectangular pulses, right? So now in full wave rectangular pulses, this probability error is still the same, okay? A is still the same, but we need to compute the power, okay? With full wave on-off keying pulses, then the power equation is different, right? The power equation now is A squared over 2, isn't it? Right, A squared over 2. If you refer to the lecture notes, I actually did the summary for you. So it's A squared over 2. Then you see that the power required at the receiver is 46 microwatt. All right, if you convert to dB, it will be about 43.37 dB. Okay, and again, to calculate the power at the transmitter, you just add 30 dB. All right, or actually this one multiplied by 1000, then you get 46 milliwatt.
Done, Miss.
Okay, so 4C and 4D is the same calculation that you need to do, but except that now you are actually working on polar half-wave houses and polar full-wave houses. All right, this one I'm going to leave it to you to do it. Okay. Yeah, and then we'll discuss the answer the next time we meet. So for question number 5. Question number 5. Question number 5, I think I'll leave it until the next time because it's quite long. Okay, so any questions so far? Right, you can see that as far as digital communication is concerned, I think I mentioned this before, the calculation is actually very easy when the equation already short. But you must know your concept well. If you know the concept well, then the calculation is actually very, very easy. No question? If no question, then we may end the class here. Question 2, okay? What about question 2? Uh-huh.
Hello, Miss.
Yeah.
Just now the question 2. Last time during your lecture, you say the constellation diagram, the y-axis is sign. Is it the positive sign and negative sign? But why the question 2b? When you're drawing the binary, the bit 1 you are actually drawing a positive sign instead of negative sign. The constellation diagram is showing negative sign. It is located at the negative A, which is the negative sign. But last time during the lecture, you are drawing.
Oh, okay. I see your concern. Yeah, I see your concern. Okay, now, when you do a phase shift, all right, if you refer, okay, let me share my screen first. Okay, if you look at this question, the 0, 1 is transmitted cosine plus pi over 2. Cosine plus pi over 2. And cosine plus pi over 2, that means we need to actually shift, we actually plus pi over 2. So in terms of shifting property, that means we need to shift this pulse to the left hand side. To the left hand side.
But last time the
correct. Last time the lecture, okay, let me write it down somewhere here. Okay, this one
is the Qpsk one, the lecture.
Yeah, I know. If you are talking about, it depends on your phase angle. Is it minus or plus here? Is it positive or negative? So if I'm talking about negative pi over 2, this one is minus pi over 2, then yes, I'm sending a sine wave in place of a minus sine wave.
Oh, okay.
Yeah. This
Okay,
sign
that's
matter. Okay, all right, good.
Thanks.
Yeah, thanks for pointing that out. Yes. Okay, anything else?
Miss, I want to ask, will we have having class on week 12?
Do we have class on week 12? Why? Why you ask? I think we will have.
Because of we have the FYP oral presentation like clash with it, so I'm not sure will you have class or not?
You can arrange your FYP at the time.
Okay. Okay, thanks, Miss.
Yeah. I think we'll have class. Week 12 only, week 14 maybe no lah, but week 12 we should still have class. Because I believe you have a lot of questions on your assignment to ask by then. All right, so I will have the class for you to ask questions. All right, for me to address some of the problems that you might encounter during your assignment attempt. I think I will not go into new chapter yet because you must make sure you are able to do your assignment. All right. Okay, and if you actually talk to your senior in the past, they'll probably tell you that the assignment question will be useful if you're able to do your assignment questions. When you go to the final exam, it will be very easy for you. All right. The final exam question will be a simple version of your assignment question. So you must be able to do your assignment in order to do your final well.
All right, thanks, Miss.
Okay. All right, anything else? If not, then we'll end the class early today. I don't really want to rush and squeeze and discuss everything, rush through all the things. Because your concept must be strong and correct, for you to do this question on this chapter properly. Okay, so make sure you go through the question 4, the part C and part D on your own, because then only that will you understand better. Okay, if not, then we end the class here.
I found something again.
Yeah, Xingwei.
Can you let me share my screen first?
Sure.
Okay, this is the lecture last time. So you can see here 0, 1, 0. It is without phase shift, right? It's at 0 degrees, so it is a cosine wave at here. You see, and then but then if you just like you say if the phase shift is negative 90 degrees, so it's 1, 0, 0, right? Is at here, then negative 90 degree. So 1, 0, 0 is here, so it is a negative sign. If it is phase shift, what am I talking? A bit kanjiong.
Cool down.
The ballet lah. I mean is, you see 0, 0, 1 is like
1, 0, 0 is negative sign, yes.
Yeah, you are drawing,
Negative sign,
you are
yes.
pointing at negative sign, but you see this graph, it is actually phase shift 90 degree of the cosine, not negative 90.
Phase.
It's actually you are delaying. I mean, no. You are wait let me think let me think first. Today a bit blur on me. You see, this is the delay version of cosine, right?
This is cosine,
Yeah, a delay version. The delay 90 degree of the cosine.
This is
But
sine.
you are but you are pointing at the or at the at this part, the sine part.
If you look at this one, this is shifting to, this is a sine wave is cosine.
Zero 1 0 is cosine 0 degree, right? 0 degree. So it's point at here. 0 0 0 is 90 degree, which is here, but this is not 90 degree. This is negative 90 degree.
Minus. So this one, I'm actually shifting the cosine wave to
the right.
I'm shifting the axis to the left-hand side.
Yeah.
I'm shifting the axis to the left-hand side, meaning I am minus.
Yeah.
I am minus.
So the balik lor.
Oh yeah, you're right. Okay, let me work this out again, and then looks like you're right here.
No, I'm confused about this.
Okay. I see your point. Okay.
But the cos, the x-axis don't have any problem, only the y-axis.
So it's only a matter of plus pi
Yeah.
over 2 or minus pi over 2, right?
But just now the tutorial seems like you are correct, but after I revise back the lecture, I don't know a bit confused .
Okay, so it's matter of plus or minus sine over pi over 2. Okay, if you are shifting the axis to the left-hand side, shifting the axis to the left-hand side, meaning as far as shift is concerned, you are minus plus. Wait. So now my cosine is like that. My cosine is like that. So if I were to shift to the left-hand side, theta plus 90 degree plus 90 degree, that means I'm going to need to shift my theta need to be minus 90 degree. Okay, so that one I'm actually shifting to the shifting my axis. So when theta is 0, then cos theta is negative. Yeah. And if theta is 180 degree, that means my cos theta is 90 degree, then will be cos 180 degree. So cos 180 degree is -1, right? Cos 180 degree -1, yeah, that is correct. So that is, so cos of theta plus 90, so that will give me this graph. Cos theta plus 90 will give me minus sign. Ah, I see.
Okay, what about you share your screen?
Wait, I'm working on paper. So cos
Okay.
theta plus 90 degree will give me minus sign. But cos theta minus 90 degree will give me plus sign. Right, cos theta minus 90 degree will give me plus sign. So that means yeah. Can I get back to you?
Okay, no problem.
This is about the lecture slide, right? But I don't think my tutorial question is wrong. I think maybe this one
Yeah, I also
interpreted
think
wrongly.
so.
Yeah, I think it's a QAM that interpreted wrongly. Okay.
Okay.
I confirm with you next lecture. Can?
Okay.
Yeah, okay. Okay, anything else? Tak ada? All right. If no time, then we end the class here lah. Okay. Bye-bye. I'll see you in your next class, yeah?
Thank you, Miss.
Thank you.